Welcome to Learning with UNP. In this session of Data Science and Mastering Machine Learning, we are going to understand about support vector machine. That includes understanding about what is SVM, key terms of SVM, working of SVM, examples of SVM, types of SVM, kernel trick of SVM, and finally understanding about pros and cons of SVM. We will also work on two projects implementing SVM. Let's begin with understanding about what is SVM. A support vector machine (SVM) is a type of supervised learning algorithm used in machine learning to solve classification and regression tasks. SVMs are particularly good at solving binary classification problems, which require classifying the elements of a dataset into two groups. SVMs are also used for linear or nonlinear classification, regression, and even outlier detection tasks. Over here, let me tell you the objective of SVM. The main goal of SVM algorithm is to find the optimal line or plane that separates data points into different groups based on their features. As you can see on the screen, the graph shows red points and blue points. Let the points with red color be class 1 and the points with blue color be class 2. To sort these data points with two features x1 and x2 into red or blue classes, SVM finds the best line that separates them. The best line is the one that creates the biggest gap between the red and blue points, ensuring they are as far as possible on either side of the line. Let's now look at the key terms of SVM. These include hyperplane, support vectors, margin, kernel, hard margin, and soft margin. Let me explain you each term clearly. First comes hyperplane. A hyperplane is a line or surface that separates different groups of data points. In simple cases, it can be a straight line. Second comes support vectors. Support vectors are the data points closest to this separating line or surface. They help decide exactly where the line or surface should be placed. Third comes margin. The margin is the space between the separating line or the surface and the closest data points. The goal is to make this space as wide as possible, which helps improve the accuracy of the classification. Fourth comes kernel. A kernel is a function that helps the SVM algorithm handle more complex data by transforming it into a higher dimensional space. This makes it easier to find a good separating line or surface. Examples of kernel includes linear, polynomial, RBF, that is radial basis function, and sigmoid. Fifth comes hard margin. A hard margin is a strict separating line or surface that perfectly divides the data points into their correct groups without any mistakes. And sixth comes soft margin. A soft margin allows some mistakes in the separation, which can be useful when the data is not perfectly separable or has some outliers, which are errors. It finds a balance between making the margin wide and minimizing the mistakes. As you can see on the screen, there is a graph displaying red and blue points. Let's use this graph to understand the terms. In here, there are three lines labeled as L1, L2, and L3. L1 represents the support vector. These are the closest points to the line that separates our data groups. They help decide exactly where to draw the line. L2 represents the hyperplane. This is the line that separates our data into two groups. It is placed to maximize or increase the distance from the closest points of each group. L3 represents the support vector. These are also close to the separating line but on the opposite side. An important point to note here is that if we remove a data point, which is a support vector in our SVM model, the position of our separating line or plane, what we call the hyperplane, will shift. Support vectors are critical because they determine exactly where this boundary should lie to best separate our data into different groups. On the other hand, if we remove a data point that is not a support vector, it won't affect our model. These points are as far as away from the decision boundary and don't influence its position. So, in SVM, the keynote is to pay attention to those support vectors. They are the ones that define how our model classifies the data. Let's now understand the working of SVM. Step 1. Data collection. First, gather the data that includes points or examples of things you want to classify. Step 2. Kernel selection. Use a suitable kernel function that helps in deciding how to change the data so it's easier to draw a line or plane between different groups. Then pick a method that works best, either a simple straight line or a more complex way that can handle curvy shapes in data. Step 3. Data transformation. Apply the chosen method to convert original data into a new format where patterns are easier to detect. Step 4. Hyperplane construction. Calculate the optimal line or best line or plane that separates different categories into the transformed data space. Step 5. Margin maximization. Adjust the hyperplane to maximize the distance from it to the closest examples of each category, ensuring clear separation. Step 6. Soft margin handling. Allow for some examples or data points to be on the wrong side of the separation line or plane, balancing between accurate separation and flexibility. Step 7. Model training. Train or teach the model by feeding it many examples with known categories so it learns to classify new examples correctly. Step 8. Model evaluation. Test the model's accuracy using new examples that were not used in the training to see how well it can classify unknown data. Step 9. Use the trained model to predict the category of new examples based on what it learned during training. And finally, step 10. Deployment and maintenance. Implement the model in real world applications and regularly update or improve it to maintain accuracy over time. Now, let's understand SVM better using few examples. I'll explain what happens before applying SVM and after applying SVM. The first example involves a graph with two groups of points colored in red and green. Before applying SVM, we have two separate groups of data points shown on a graph, but they are not accurately classified into red and green dots. Visually, the groups appear different, but some points may overlap or be misclassified. After applying SVM, it works through several key steps to classify data points into different groups like red and green dots. First, it starts by drawing a line or plane to separate these groups. Then, it identifies support vectors, points closest to this line. SVM calculates a margin, the space between support vectors and the line, aiming to maximize it. Then SVM finds the best line that maximally separates the groups, potentially using a kernel to handle complex data. After determining the best line, SVM classifies each point as red or green based on its side of this line. We also have second and third examples. As we have seen before for the previous example, almost the same happens here too. In the second example, SVM classifies the data into two classes, red and yellow. The algorithm separates these groups using a clear line or plane, identifying support vectors, maximizing separation margin, and adjusting the line's position for optimal classification. In the third example, SVM categorizes the data into green, yellow, and blue classes. It does this by drawing the separating line or plane. It identifies support vectors, optimizes the margin to maximize the separation, adjusts the line's position for accuracy, and uses kernel to handle complex data. SVM ensures each data point is correctly classified into green, yellow, or blue based on its position relative to the separating line. Now let's look at the types of SVM. The first type is linear SVM. Linear SVM is a type of support vector machine that is used when data can be separated into different categories by a straight line or hyperplane in a higher dimension space. It works well for the data that is easily divided by a clear boundary, like sorting apples and oranges based on their size using a single straight line. Here is a graph with data points represented by two different colors. With linear SVM, the goal is to draw a straight line or a hyperplane that best separates these two groups. Here, the SVM drew a line that best separated the data points into two different classes with different colors in each class. The second type is nonlinear SVM. Nonlinear SVM is a type of support vector machine that is used for data that cannot be separated by a straight line in the original feature space. It uses kernel functions to transform data into a higher dimensional space where a linear separation is possible. This method enables SVM to handle complex patterns and relationships in data that are not linearly separable. Not linearly separable means if you cannot draw a single straight line on a graph that cannot separate two different groups of data points, then those data points are said to be non-linearly separable or not linearly separable. SVM can handle examples such as distinguishing between different shapes like circles and squares, etc. In here also, we consider a graph where the data points are represented by different colors, but this time they are mixed in a way that no straight line can perfectly divide them. Here, nonlinear SVM comes into play. It uses complex mathematical function like kernels to transform the data into a higher dimensional space where a linear separation becomes possible. Let's say it might map the points into a space where they can be separated by a curve or more detailed boundary, improving the accuracy of classification beyond what linear models can achieve. Now, let me tell you in detail about kernel functions that we use in SVM. First comes linear kernel. The linear kernel calculates similarity between data points by measuring how close they are in the original feature space. It is used when the data can be separated by a straight line or hyperplane. For example, it's like drawing a single straight line on a graph to separate two different groups of points. Second comes polynomial kernel. The polynomial kernel function transforms into a higher dimensional space using polynomial functions. This transformation helps SVM classify the data that is not separable by a straight line in the original space. It's like mapping points into a space where a curved boundary can better distinguish between different groups. Third comes radial basis kernel. The RBF or radial basis function kernel measures similarity between points based on their distance from each other. The RBF kernel looks at how far apart data points are from each other. By measuring this distance, it creates a new way to view the data, a space where complicated patterns are easier to spot. This helps SVM classify things like different types of animals based on complex features that might not make sense in a simpler view. Fourth comes sigmoid kernel. The sigmoid kernel uses the sigmoid function to measure similarity between data points. It transforms data into a higher dimensional space where SVM can find patterns that are not linearly separable. This kernel is less common than others but still can be effective in certain scenarios where data exhibits complex nonlinear behaviors. Finally, let's look at advantages and disadvantages of SVM. Advantages of SVM are SVM works well when there are many features. SVM performs best when classes are clearly separated. SVM can handle different types of data by using various kernels. SVM tends to generalize well to new data. In SVM, only the important data points support vectors are used. Whereas disadvantages of SVM are SVM can be slow with very large data sets. SVM struggles when there is lot of overlapping data or noise. In SVM, choosing the best kernel for the data can be tricky. The performance of SVM depends heavily on parameter settings. And finally, SVM may not perform well if the data set is extremely large. This is all about today's lecture. See you in the next lecture. Thank you.